Now Chris will tell us about collaborative generation of code-based SNARKs.
Yeah, code-based collaborative SNARKs. Okay. So, hello everyone, I am Chris. And today I will talk to you about code-based scalable collaborative SNARKs, and this is a joint work with my advisor Dimitris and Pappas. Okay, I will start now with something that you probably have never seen before today, ZK SNARKs. So, ZK SNARKs are cryptographic protocols between a prover and a verifier, where the prover wants to convince the verifier that it knows a witness W that satisfies an NP relation and generate a small and easy to verify proof. Now, importantly, ZK SNARKs are zero knowledge in the sense that the verifier learns nothing about the witness of the prover. And of course, they have tons of applications. They have been used to anonymize transactions, validate the correctness of machine learning model inference, and most recently, zero knowledge identity. And in all of these applications, in fact, zero knowledge matters. For instance, to anonymize transactions, the prover wants to generate a proof that about the correctness of transactions without revealing payments data. Or in the ZKML, he wants to prove the inference of a machine learning model without revealing the model itself. And in ZK identity, he wants to prove claims about itself without revealing its personal data. Now, while ZK SNARKs do a very good job on protecting the privacy of the verifier, unfortunately, they don't do so for the prover. And that's because the prover, in order to generate the proof, he must hold the entire witness. Unfortunately, in some cases, this is undesirable. For instance, there might be a party that holds the entire witness, but it doesn't have the resources to generate the proof, like we saw in the previous lecture. Or we might have multiple parties who hold only part of the witness, and they want to jointly construct a ZK SNARK over the entire witness. And in these two applications, in order to generate a ZK SNARK proof, they must offload the proof generation process into another party. For instance, in the first case, the computationally constrained device, it has to send the witness to a server, or in the second case, all the parties need to select a single party in order to act as a prover. And of course, they will have to send the witness, which would violate the privacy. So, from what I can think, there are only two ways to overcome that issue. The first one is to let the parties encrypt their data using a fully homomorphic encryption scheme, and then let the prover generate a ZK SNARK proof over the entire encrypted data. And while this approach is optimal in the sense that it requires only a single server, unfortunately, it is highly impractical because now the prover has to work over the encrypted data. Now, the second approach, which is the main focus of this work, is to use collaborative SNARKs. And these are like a generalization of ZK SNARKs that enable multiple provers that hold only part of the witness to collaborate using an EPC protocol in order to generate a ZK SNARK proof. And co-SNARKs must have the same security properties as standard ZK SNARKs, but also they should be T0 knowledge, in the sense that up to T provers should learn nothing about the witness of the honest ones. Okay, so most of existing co-SNARKs focus on adapting existing ZK SNARKs in the collaborative setting. Unfortunately, the vast majority of these works are not scalable. In other words, the per prover time complexity is proportional to the circuit size, which means that we get no efficiency benefit of running a co-SNARK, but only the strong security guarantee. So as you can see from this table, while non-scalable co-SNARKs have very good verifier complexities, which is constant or logarithmic to C, or total communication cost, or excellent security threshold, which is all but one secure. Unfortunately, the per prover time is quasi-linear to the circuit size. In fact, there are only two works that actually try to construct scalable co-SNARKs. And as you can see from this table, the per-prover time complexity is inversely proportional to the number of provers. So we don't only have a very good security guarantee, but also the more provers we have, the smaller the prover time. Unfortunately, these two works have some limitations. First of all, the initial work does not support efficient multiscalar multiplications, and so it is concretely very, very slow. Now, the second work, which is compianist, while it overcomes the limitations of the first work and also has a better security threshold, unfortunately, it has concretely large communication cost. And also, those two works are not scalable, are not transparent, and not post-quantum secure compared to some non-scalable co-SNARKs. And that's because they rely on elliptic curve-based polynomial commitment schemes. Now, in this work, we introduce the first transparent and post-quantum secure scalable co-SNARK, which is based on codes. And our work is also concretely more efficient than the previous ones because it is dominated only by field operations. And also, for the state-of-the-art security threshold, we have concretely smaller communication cost. Okay, so before diving into the details of our construction, let's see how in general we construct collaborative SNARKs. For this, we follow the standard POP plus PCS paradigm. However, we adapt it in the collaborative setting. This means that in the commitment phase, the provers interact over an MPC protocol in order to compute the polynomial commitment of the joint witness. Then, again, using an MPC protocol, they produce a POP proof, which in essence reduces a claim about the circuit satisfiability to a claim about the correctness of the evaluation of the polynomial commitment. And finally, they run an MPC protocol, generate an opening proof that validates the correctness of that claim. Now, recall that our goal is to construct transparent and post-quantum secure co-SNARKs. And one way to achieve this is to try to adapt code-based ZK SNARKs in the collaborative setting. In practice, in the commitment phase, we need to run an MPC protocol that emulates the encoding of a linear code and then sends the oracle to the verifier. And then in the opening phase, we need to run an MPC protocol for an IOPP to prove that the committing message is close to an actual encoding, and also the polynomial that derives from this message actually correctly evaluates at the specific claim. Unfortunately, although these two tasks, while they seem simple, they are not so trivial. For instance, while we know how to construct MPC protocols that compute some code words over the joint witness, unfortunately, existing solutions are not scalable or they have large communication costs. And in this work, we first of all introduce zero-knowledge collaborative codes that, in some sense, generalize zero-knowledge codes the same way as collaborative SNARKs generalize standard ZK SNARKs. And then we show how to build a collaborative code which is based on Reed-Solomon tensor codes that is both scalable and has minimal communication overhead. Now, for the POP, while we have scalable co-POPs, either they have large communication costs or low security threshold. In this work, we construct a scalable co-POP for Argo1CS based on the Spartan POP, and then compared to prior works, it is faster and also it has smaller communication overhead. And finally, regarding the collaborative IOP, while we know that some collaborative IOPs already exist, unfortunately they have large proof size, which is proportional to the number of provers, and also the total communication cost is again proportional to the entire witness size. And in this course, we formally define co-IOPs, and in fact show how to make them non-interactive using the BCS transformation, but adapted in the collaborative setting. And then we construct a scalable co-IOP from our code that has logarithmic communication cost and also polylogarithmic proof size. Okay, let's begin with our main building block, which is the collaborative codes. Formally, collaborative codes enable multiple parties who hold only part of the input to jointly compute a code word, possibly using an MPC protocol, and at the end of the day, each party ends up with a segment of the entire code word. Now, security-wise, collaborative codes need to be T, L zero-knowledge, in the sense that up to T corrupted parties should learn nothing about the inputs of all other parties, and this is done even if they query L elements of the code word. So let's see now how to, in a generic way, to construct collaborative codes. For this, the parties first secret share their inputs, and then they run an MPC protocol that emulates the encoding functionality of a T0 knowledge code. And at the end of the day, each party ends up with a secret share of the code word C. Unfortunately, this approach has some limitations, okay? First of all, performance-wise, if we use standard secret sharing, then although we have minimal communication overhead, which is only just to secret share the inputs, the encoding time of each party should be proportional to the entire input size. Now, on the other hand, if we use packed secret sharing, then although we achieve scalability, unfortunately this approach has large communication costs and possibly a large number of communication rounds. For instance, if we use the best MPC protocol for scalable computing and read Solomon code, then the provers would have to communicate over log n rounds, and in each round they should send total amounts of data that are proportional to the total input size. Next, and most importantly, it is unclear how to construct co-IVPs that are efficient in terms of proof size. And that's because the verifier, if he wants to perform a point query over the code word C, then it would have to point query each secret share of C, which would blow up the proof size by a factor of n. So let's see how to construct a collaborative code that overcomes all of the above limitations. So the key observation is that Samir's packed secret share of a vector is in fact a read Solomon code word with a large constant distance. So let's see how to use it in order to construct our code. Initially, we have the same test setting where each party has its own part of the input, and beneath we have the global view of each party. Now, as in the generic approach, all parties secret share their inputs using the Samir's packed secret sharing scheme. And now, in the global view, what we have is actually a code word, which is an interleaved code where each column is actually a read Solomon code word of size n. Unfortunately, this code word has very, very small distance, which is in fact non-constant. However, now each party holds only one row of this code word. So in fact, it is possible to compute a tensor code out of this code word by simply locally encoding each row. Okay, and so we let each party encode the row using a constant and linear code that has a large constant distance, and in this way we end up with a tensor code that has a constant distance. And in fact, in this work, we use a collaborative code that consists of a product of two read Solomon codes. And this way, the per party complexity is m log m divided by n, where m is the global input size, and communication complexity-wise, it achieves a single round of interaction with a total communication cost of OM. And in fact, this communication overhead is only just to secret share the inputs, and in many applications, the parties would already have the packed secret share, so this cost should be omitted. And finally, and most importantly, now each party holds a row of the tensor code and not the secret shares. And looking ahead, this is important because we want to construct efficient co-IPs. So let's see how to construct now a collaborative IOP. And here we will focus only on proving the proximity of our tensor code. Now, the key observation for this part is that Reed-Solomon tensor codes are actually foldable, in the sense that there exists a folding functionality that takes as input the code word, a random point R, and actually compresses the original code word into another one that is Reed-Solomon tensor code. And now there are many ways actually to construct this folding functionality by folding the rows, the columns, or both. And in this work, we actually use the folding algorithm for the Reed-Solomon codes to encode each row of our tensor code. And this enables us to adapt the FRI protocol over Reed-Solomon tensor codes and in the collaborative setting. In particular, the provers first hold their own row of the tensor code and then send the oracle of the code word to the verifier, and the verifier sends a random point R1. Next, the provers use this R1 in order to fold locally their own part of the tensor code, send the new tensor code, the oracle of the new tensor code to the verifier replies with another random point, and this continues recursively until we end up with a constant-sized code word. Next, the verifier does the same queries as it does in the standard FRI protocol. Unfortunately, this protocol is not T0 knowledge, and that's because the queries done by the verifier over the folded code words might leak some information about the original message. So one way to overcome that issue would be to simply use the techniques of zero-knowledge FRI protocols and mask the original code word with another random code word. However, this would be very, very expensive because now the provers would have to collaborate in order to generate a random message that has the same size as the original message. And this would blow up the communication cost to proportional to the input size. And the way we overcome that issue is to simply mask the code word on each iteration. However, the randomized code word we use to mask on each iteration has only derives from a message that has only a few elements that are enough in order to make the entire protocol T0 knowledges. Okay, so this is only part of our contributions. You can see the paper for a formal definition of co-IOPPs. Also, we saw how to make them non-interactive using a collaborative variant of the BCS. And interestingly, our construction is also secure against malicious provers. And we had to do some modification because if we do it naively, then the provers might perform some attacks that violate T0 knowledge. And also, we construct a co-POP based on the Spartan POP, as I told before. And for this, we use the grand product argument of Thaler 13. And naively, to do that, you would have to use log square communication rounds. However, we reduce that to log n by proposing a new distributed sum check that has only a constant number of communication rounds. Okay, let's now go to the benchmarks. We implemented our core SNARK in C++. We used the field extension of 61-bit Emerson primes. For the communication between the provers, we used the MPI library. Next, we benchmark our scheme into two different network settings, a LAN with 2 milliseconds of round-trip delay and a one with 100 milliseconds of round-trip delay. And we compared our scheme with existing scalable core SNARKs and also with centralized ZK SNARK that consists of a Spartan POP compiled with a weird PCS. Let's start by benchmarking only, first of all, our scheme. From left to right, we have the prover time with increasing number of provers, and in the right, we have the prover time with increasing circuit size for the two network settings. And as you can see, in our LAN setting, our scheme achieves almost perfect scalability. Now, it becomes slower in the one setting, by at most 5 times, and that's because of the logarithmically many rounds of communication between the provers. However, if we increase the instance sizes, then the overhead of the communication becomes smaller and smaller. And finally, it's okay, our proofs are quite large, but there's lots of room for improvement, and we have a good verification time. Let's now go to comparisons with other SNARKs. From left to right, we have, again, the prover time per increasing circuit size, and on the right, we have the total communication cost for a varying circuit size. Our SNARK is 2 to 10 times faster than Copianist, and here we don't include the first work because it's already at least 3.5 times slower than Copianist. And regarding the total communication cost, it is 13 times smaller than other SNARKs. Finally, remember that the whole reason to use a scalable SNARK is to have an efficiency benefit. So let's see if we can achieve that. So here we have the prover time, again, increasing the number of increasing circuit size, and we compare our scheme with the centralized ZK SNARK. As you observe, our scheme outperforms the centralized ZK SNARK even when we have more than 8 provers, even in the one setting. And in fact, in the last setting, it achieves an optimal n divided by 4 improvement. And of course, this improvement can be further improved if we use a better security threshold. If we use a lower security threshold, better. So, okay, conclusion. We constructed the first scalable, transparent, and post-quantum secure SNARK. Our scheme outperforms all existing schemes, and some future directions are to decrease the proof size, and this can be done by using better proximity, finding actually better proximity gaps for Reed-Solomon tensor codes, or removing the masking per FRA iteration in a meaningful way. So that's all from me. Thank you.
Questions? So I just like to ask if you go way back to what you called the key observation.
This key observation or from a...
No, I think there was a previous. Yeah. So, first of all, just to make sure I follow. So, what do you mean by packed Shamir? A packed secret share? Just so I'm sure.
So in standard Shamir secret share, you just secret share a single element, right?
Each party has a single.
So you have a polynomial. You construct a polynomial, a randomized polynomial. You interpolate that polynomial, and then the shares are But the pact in the Shamir packed secret share, you do the same, but for a vector. So you can say you want actually to secret share a vector and not a single element, in order to actually amortize computation cost. Because if you pack secret share a vector, then you can have scalability. Because in some sense, you can parallelize the computations that are done over a vector, because each party will...
So how do you do? So you want to share a vector? So one way is to just independently share each...
If you want to share a vector, then you just take the vector, you add some randomness, which depends on the security threshold, and then interpolate the polynomial that is derived from this large vector. This large vector would have actually size n divided by 2, for example.
And you still give each party just one field element?
I mean, yes. Assume that the entire vector would have n divided by 2 size. Then you interpolate it, you compute the polynomial, and then send to each party an evaluation of this polynomial.
So if the party is just getting one field element, why is the share RS code word with constant distance? You say here the secret share. You say if I parse the size.
I mean all the shares together. I mean the shares of all of all parties. I mean, if
Oh,
we
the
take
shares
all the
together.
shares,
Okay.
yes, yes, yes.
All right, all right.
I mean, that's why
Yeah.
each party has only a row at the end of the day. So this would be the entire share, and each party would have only one element of that share.
Right. Wait, but what are they? Right, they're starting. Each one has part of the witness, right?
Yes.
So what are they? What are these shares? Like, what are they sharing exactly?
Okay. Now each party will break down this vector into smaller vectors, and then use a pack secret sharing scheme, and will send one element to each party. We'll just pack secret share.
Oh, wait, sorry again. So these W's, they are the witnesses of each party, or
Yes, I mean
the W's are the parts of the witness.
yeah, yeah.
Okay. And now, okay. So now again, what are you sharing?
Yeah, I mean, each party will share this vector to all other parties using a packed secret sharing scheme.
Oh, okay. Each party is sharing.
Yeah,
the,
yeah, yeah.
The okay. And what is it in what version of like how many parties need to? Okay, sharing with some threshold where okay.
I mean, you can do it with threshold n divided by 2. If you use a threshold n divided by 2, then you will have the distance of the Rich-Solomon code would be 0.5. If you use the lower threshold, then you increase the distance.
Right,
but
right.
you decrease the security threshold.
I see. Okay, and any other questions? Okay, let's thank the speakers again.
And thank you for chairing this, these talks. All right, so that was our last session for these 2 days, and we wanted to take a few minutes to, to wrap up and say all the thank yous that we wanted to say. So for that, Alex, Vivek, please join me. So our job is in 5 minutes to try to figure out how to say thanks to all the people that made it happen. First and foremost, it's a big thank you to you, Alex, and the Ethereum Foundation for being the main sponsors for this event. So please, a big thank you. Maybe you want to say a word?
Yes, thank you to the EF.
Indeed.
But, well, obviously, thank you for organizing this, because you've been doing this for many, many years, and I think the community has greatly benefited from these events. Thank you to everyone who's come and given a talk, and listened to talks, and asked questions, and talked in the hallway, and all of this, and the crew who runs the live stream, or 3 live streams in parallel. Jens and Michelle, who obviously organized the PC, and there were many more papers this year than other years, and so it's probably much harder than what they thought they signed up for.
Vivek and I are currently running a bingo in our head of like the people you're thanking that we also want to thank, so we're joining that, yes.
So thank you also to Vivek for keeping, making sure that I actually set a schedule for our clip day, doing Zoom with Kwong. Obviously, thank you for having Kwong on as a remote speaker. Thank you to, I guess, the hotel staff as well for nothing went wrong. Wi-Fi, food, everything, it was great. Thank you to the air traffic control people in Rome who are striking tomorrow when I'm supposed to leave. That one is not appreciated. There's an air traffic control strike tomorrow.
Oh, they're learning it now. Don't worry about it, don't worry about it. We'll talk about it later.
Ask your airline. Some things are cancelled. Some things are just going to be delayed. I don't know.
Your mileage may vary, right?
But I've come to Italy twice in 1 month, and both times I've had air traffic control strikes. So great. We can do another country next time. Yes, I guess Dan, Justin, all the post-quantum stuff is really exciting, and I'm happy we're having these sessions and getting the latest and greatest and getting excited about all of this. Yeah, you can say it. I think that's about it, I think. Thank you to Gregor, giving a great talk about clean. There we go.
Yeah, I think like Alex covered like most of the stuff that we wanted to thank, but also I think like ZKproof is like a team effort, and I also wanted to shout out to Liad, who's not like
Yes.
physically present, but she did a huge amount of the logistics, setting up the hotel and everything beforehand, and she was like very available during the event as well to like help us out wherever it was needed.
Why is she not
And-
here? Why is she not
Yes, congratulations to Liad.
Yeah, she recently like gave birth a few months ago, and so she's she's there like with a young child, so she's like
probably seeing us? Thank you.
yeah.
Yeah, thanks, Liad, if you're seeing us.
So yeah, like I also wanted to thank again Jens and Michelle and all the program committee for like we got lots of papers. I think it was a tough job to like pick only 40 of them, and yeah, that 40 made it like pretty packed, but I still think time has flown by, and I hope like everyone had a bunch of fun.
So how many people in the program committee?
There were 22, I think, by the end. Yeah.
A lot, right?
And
So 20 different people, which is the reason why we're not saying their names, but thank you all for reviewing such a great amount of excellent papers. And also the people that submitted those papers.
This is true, actually. All the submissions were basically good, which I know is not common. And so actually reviewing the papers was not a pain. So thank you for that.
So yeah, I also wanted to thank Yaniv and Ruthie. They do like the websites, the slides, all like everything goes like super well thanks to like everything being clean and looking good. So thanks to the AV team. It's no easy job to like make sure everything's working smoothly, and like y'all have done really great, and we get like great talks every year. So thanks a lot for that. And
thank you, Ronan, for taking only my right side and not my. Basically, for knowing all of the right terms in zero knowledge and the industry. You're giving a talk, okay. So the application for papers is for the next one. I want to just say by name. So the Ethereum Foundation, Kedit, Financial Privacy Inc., Inverse Tech, Solana Foundation, and the Zcash Foundation. That's our sponsors for this event.
Yeah, and I think like the first time I came to a ZKproof was back in 2019. And like just as a grad student with trying to get a feel of like what to do in zero knowledge, what are the problems to work on. And yeah, now I think I have a better feel for the area, but what to work on now is I think more of a problem of plenty. And I think thanks for that goes to like all of you for making this such a like vibrant and dynamic community with like so many papers coming out, so many like good quality research directions to work in. So yeah, thanks a lot for coming here, and yeah, whether it's your first time or it's like you've been here for even longer than I have, like I hope to see you again next year, the next iteration.
Joining that, see you all very soon. Thank you.